Hello, hello. Good afternoon. Good afternoon. All right, good. Oh, here we go. Okay. So, good afternoon, Chastity. Good afternoon, Annie. Good afternoon, Yanelli. Good afternoon. That's the video. Good afternoon, Kaya. So that's the visual. Here we go. Wait, sorry. Good afternoon, Brian, who I know was first. But I was doing the visual first, but I totally see you. Good afternoon, Yanelli for the double. Good afternoon, Chastity for the double. Good afternoon, Kaya for the double. Good afternoon, Annie for the double. Good afternoon, Genesis. Good afternoon, Natalie. Good afternoon, Carlos. Good afternoon, Ariana. Yes. Good afternoon, Sydney, with the exclamation point. Thank you for the enthusiasm. 2 semesters later, and there's still enthusiastic punctuation marks. That's awesome. Okay. Even though I'm sure the hatred is high right now, or no, I'm so you, some of you may have noticed the exams are coming. Oh, no, wait, here. I'll talk about 2 semesters. Hold on 1 second. Whoa. Oh, a lot of two. Okay. I'll pause for a second. Excuse me. Okay. So good afternoon, Gabriella, and good afternoon, Skylar. So I was just saying, so the exams are continuing to come back. Some of you will have noticed that you got an exam back. Many of you still have not. This is true in all the classes. I'm sorry, I'm not gonna, they're coming. They're just coming very slowly, but they just each time I finish one, I just send it back. So I haven't finished them all yet, and I recognize that's super annoying. And it's also annoying for me to talk about it so much. I get that. So, but they're coming and they'll continue to come, and you will eventually, and they're not in any order. You'll get yours when you get yours. I'm going to just keep working through them. And they're fine so far, whatever. But one thing again, I think I mentioned this last semester when I went through this last semester with you. And you will get them in time to know what to do for your final exam. Um, but also, if for any reason, I'm just putting in the chat, if this is making you edgy or anxious, which of course it is, I mean, which of course I understand. Um, we're just putting in the chat. Hold on a second. Just remember, you can text me at that number or email me and just say, I'm getting anxious. Can we schedule a 15-minute phone call to talk through my standing of this class or something, or or something like that, or depending on where I am when you and we could just talk while I'm in the car getting back and forth to New York, or if depending, I could sit down and put your exam to the top of the pile if it's starting to become like a real situation for you. What just you can reach out and I'll understand and I will try to meet you wherever you are, if that makes sense psychologically. I mean, I can only get through the exams as fast as I'm getting through them, but if it's starting to cause you like a thing, then just reach out to me and we'll talk through the thing, whether that means literally with the exam in front of me or not. Okay, just say so that's a bit okay, I hope that's clear. So I apologize, but they're continuing to come or go. And the order in which you get it reflects nothing other than like where your first name is in the alphabet of all my classes or something like that. Okay, but some people have gotten them. But okay, all right. That said, I want to go back to the material, the physics. The strange thing is we're in a topic now that is like very abstract, but it's like one of my favorite topics. I can't even tell you why. I love this topic of flux, electrostatic flux, and like everything else. So I want to get back to it. And specifically, this is in the context of homework number, I think it's 7, the Gauss's law homework that I guess is due in 2 days. I can never remember. Is it? Is it? And if it is it due in 2 days or is it due Monday? Wait a minute, hold on a second. And we can be flexible about it. Obviously, I'll be very anything that is on your end right now, I will be very flexible about because I know there's something big on my end that you're waiting for. But wait, I'm just checking again. I did this in the last class, but the Gauss's law homework. Probably someone's telling me in the chat as I'm looking. I'm sorry. All right, in principle, it's due in 2 days. No, due Wednesday. Thank you, chat person. Is there any reason that has to be true? No, I'll switch that right now. I'm taking time with your exam, and it's our last assignment. And I'm sorry, by the way, we still have classes next week, and then one more week, or is it? Totally losing track. We have one more week of classes after next week, yes? Like they end up like next week is not the last week of classes. Is that correct? Can you confirm or deny in the chat? I just want to make sure. 2 weeks left. Okay. Okay. So again, you definitely will have even though I'm taking way too long, you will have your midterm stuff back in time to do something for the final, but I'm going to change the Gauss's law thing right now. There's no reason I'm going to do it in the other class. Pardon me. I mean, if you've already, anyway, whatever, just to give us more. What? Sorry. And then we're going to get, so that's May 5th. Right. Okay. Pardon me for a second. But that's what I'm talking about right now is homework 7. Like everything I say in class last Wednesday and now is specifically with relevance to homework 7. And ultimately, it's all about what is ultimately known as Gauss's law. You'll see that today. Hold on, I'm just changing this, and then I don't know why I didn't do this in the other. Okay. No, yeah. Okay. So. Okay. The law I want to establish is this, but this looks a little bit like, well, this is the law I want to establish, but it's going to take me a little while to get there. And this is all, so I'm picking up, but that's going to be the conclusion. I'm picking up from where we were last Wednesday. And where we were last Wednesday is essentially the beginning of homework 7, right? So just a quick review here of what's going on. We have a positive point source somewhere in the lab or in space somewhere. That is, we have like a dot of charge, of net positive charge, like a proton is sitting there somewhere in space, right? Hold on, I'm just changing the view screen. And those red lines are the field lines. Those red lines are the field lines created by a point source, right? That's like a given at this point in our lives. Charge creates field. Positive charge creates field that pushes out, whereas negative source creates field that pulls in. The field line diagram or the field line picture from a point source is a bunch of lines that emanate, well, that radiate, literally, as in radii, that radiate out symmetrically from that point, right? Like, and they're everywhere in space, right? So the idea is when we draw a field line picture, we're just choosing some number of lines, a sufficient number of lines to represent the pattern. And we make some rule in our mind, like, okay, for every 1 coulomb of positive source charge, or for every 1 Q of positive source charge, I'm going to draw, I don't know, 8 lines. And then whatever number you come up with, you then draw as symmetrically as possible. So you sort of choose a number that is just big enough or just small, whatever, that's just big enough to demonstrate a pattern. So, so 8, because it's like an asterisk or whatever. So, but the idea is we chose a scaling factor. We're saying for each 1 dot of charge, it's going to produce 8 field lines that would come out from it symmetrically. Then, if the picture got more complicated, right? Okay. This is like a quick review of last week or whatever. If the picture got more complicated and we had like -3Q over here, then we'd have 3 times as many lines going into that dot, right? But they'd also be symmetric, they'd be radial. So you'd have like 24 lines all symmetrically coming into that dot, and then that negative dot, right? And then if the two were brought really close together, then the lines would sort of bend one another appropriately until you had one big pattern of lines that demonstrated what would happen to any test charge in the region of those point sources, right? Right. Okay, that's like field lines in general. Now, what we have here is just one dot, one point source creating field. So the field line picture, now that's like a given. I mean, we always want to draw field lines, but what it is, what is already known from last week. The question or from 2 weeks ago, the question from last Wednesday was, okay, given a point source that creates, that creates field, what would be the total amount of flux? Like, this is what we were asking last Wednesday. What would be the total amount of flux that would occur through or flow through the surface area of some globe or some sphere, same thing, that we could imagine surrounding that point source? A sphere of radius r centered at that point source. If we imagine that space, now it's just space, no material, just space. But if we imagine the space of a sphere surrounding that point source, centered on that point source, and we imagine the skin of that sphere, the outer surface area of it, we ask the question, how much flux would pass out of that sphere's surface area? That is our first example of calculating flux. Flux mathematically means total amount of field strength passing through an area of some kind. So in principle, what flux means, what flux means is you take a given area, you take a step on that area, like you step on a little tile, like a square centimeter of that area, whatever the area is. You ask yourself, what's the field strength right at this tile? Which means what? It means count up the number of field lines passing through that tile, right? Remember that once you're dealing with field lines, field strength, once you're dealing with a field line picture, whether it's on paper or in your mind, when you're dealing with field lines, it's how close they are that indicates field strength, field magnitude, right? And flux is supposed to be field magnitude times area. So you take a step on it. So if you're calculating flux in general, I'm just trying to remind you how to picture it, what to picture. If you to calculate the flux through some area is to take a step at one bit of the area, one little tile, one like square centimeter, say, to ask yourself how many field lines are coming out, passing through this area. Whatever that number is, say there's 3. You take that number of field lines, multiply it by the area of the tile. So like 3 field lines times 1 square centimeter or whatever. And you put that in the bag of your mind. And then you take the next step to the next tile. Ask yourself how many field lines are passing through this tile. Multiply that number of field lines times the area of that tile. Put it in your bag, and you step on all of the tiles. Like, this is what an integral always is, right? It's always a continuous sum of products, always. This integral happens to be this flux integral. And again, I'm just reminding you of what we did last Wednesday and what I'm reminding you of what flux is in general. Flux is the integral of field with respect to area, or it's the area integral of field. It's like any other area where you walk through a space, taking step by step by step, and at each step, asking a product, adding up all those products, and you have your total. The only thing, well, the 2 things that are sort of abstract about the flux integral, the 2 sort of new ideas is, one, it's 2-dimensional, not 1-dimensional, right? So that's why we write as a double integral. Really, if we're being very mathematically careful and rigorous about it, you could think of it as you're integrating along one axis, like taking step along the x, Then when you get to the end of that dimension of your total area, you then, make a right turn or whatever and start adding up products along the y-axis. So in effect, it's an integral times another integral. As physicists, we sort of just do them both at the same time in our mind. Instead of doing a line integral and then another line integral, each one of our steps is already, even in the infinitesimal case, it's already an infinitesimal two-dimensional step. We're stepping on tiles rather than lengths. So that's abstraction number, not abstraction, that's like new idea number one, that it's a two-dimensional integral rather than an integral, but it's an integral like anything else we ever, and that's why we sort of practiced integrals at the beginning of the semester, or you know, okay, I've already, right? So it's like the work integral, only it's two-dimensional. The other thing is that what we're multiplying at each step is a little bit abstract. It's field rather than force or something, right? And the way we're thinking about multiplying field is by looking at and counting up field lines. So we're counting up field lines for each little bit of area, each number of field lines, multiplying by the little bit of area and adding up all of those products. And that is the total flux integral that we're looking for in any situation that anybody asks about flux. Now, the situation that we asked ourselves about, the very first one that we've ever looked at here, is, here's a new abstraction or a new challenging idea. The very first area that we're looking at to calculate flux it's a very simple area in a way. It's symmetric. It's the surface area of a sphere, right? Surrounding a dot. So in a way, the situation's as simple and controlled as it could possibly be. But you might notice, and again, I'm talking too much. I'll turn the page in a moment, but I'm just trying to remind you what the setup was for last Wednesday's class, and more to the point, what the setup is at the beginning of that homework 7. The setup is that we're first trying to calculate flux through the surface area, the entire surface area of a sphere centered at a sphere of radius r, centered at a point source of positive q. The last thing I want to say about the setup, and then I'm going to remind you the answer we got. The last thing I want to say about the setup is, even though it's our first example, and yes, in most respects, it's simpler than any other example I could come up with, it is a little bit interesting that our very first example of flux, that the area we're talking about is what we call a closed area. Now, I said this last week, but please bear it in mind. The area that I'm talking about is what English-speaking people would call the surface area of the sphere. You've heard this term, surface area. If you think about it for a second, if you consciously think about the term surface area, it's like a weird term, because surface means two-dimensional region of space and area means two-dimensional region of space. Like, why would we ever say surface area? It's like redundant if you think about it, or it sounds redundant. Well, if you think about it, the reason English speaking, I mean, whether they're doing physics or not, the reason normal people ever say surface area as opposed to just area is whenever they're talking about an area that's like on the outside of some larger volume, right? I mean, this is actually a subtle point. Area itself is a two-dimensional concept. Area and surface. The word surface and the word area, I think, are interchangeable, each one individually. And each one of them measures a two-dimensional region of space. It's measured in square centimeters or square meters or square inches or whatever, right? But whenever we say surface area, we're tacitly talking about, it's a way of covering ourselves because we're talking about an area that actually exists in 3 dimensions of space, right? Like an area that's been bent or warped, like a map that has been bent or warped to start surrounding a globe. So a map, or like pardon, sorry. A map that's been bent or warped into the 3rd dimension, like occupying 3 dimensions of space and then surrounding a 3-dimensional solid like a globe, right? The skin, the map, is still a 2-dimensional region. Just like the surface of the earth, you walk around the surface of the earth, you traverse or you buy land on the surface of Earth. And what you buy is square miles or acres or whatever. Like you don't buy cubic miles. I mean, technically, you know what I'm saying, right? Like a farm is not cubic miles or yards, it's square yards. But those square yards are are enclosing a three-dimensional region like a ball, right? So whenever and the reason they're able to do that is because the area that we're talking about in this has been closed up and its ends touch each other so that the area is now a container. It is not the stuff that is contained within, but it is the container. It's the skin. Right. I mean, I'm over talking this course, but I just want to remind you before I go any further, and I'm going to make a big deal about this, like regions of space can be open or closed. When we close up a region of space, it occupies a higher dimension, but itself still measures the lower dimension. I mean, here is a line, right? It's one dimension of length, my finger, I mean. It's measured in inches or something like that, right? It's a line segment. Technically, or not just technically, like physically speaking, this line is called an open line or an open one-dimensional region of space. If I bend it so its ends touch each other and I make a ring, or I make a ring, well, if I make a ring, right? Now I've closed up the line. Now it's no longer an open one-dimensional region of space. It's a closed one-dimensional region of space. It was an open path. Now it's a closed path. Just like integrals. Remember, single integrals could be open integrals or could be closed integrals, like back from the beginning of the semester, right? Not a coincidence. Um, well, and when I close up the line and make a closed path, it's still a path. The circumference around a circle, or the circumference, or the perimeter around a square is still measured in meters, even though it's occupying two dimensions of space. You follow me? Same thing with areas. When you close up an area, you have something called a closed area. This is an open area. This is a closed area. It's still an area, but it's a closed area. It's the boundary or the skin of a three-dimensional region known as a volume, right? So, and there's a reason we really care about these things. The point of this. So I'm saying that the very first example that we do, the very first example that we're measuring flux happens to be a closed area, like a container, but it is still an area. All right, now what? So we asked, what is the flux? We asked, what is the total amount of electrostatic field strength flowing through the surface area, the closed area surrounding, bounding a sphere of radius r. And we asked for what's the net flux and just note convention, any lines that, if you're talking about closed areas, like I just made a big deal of, if you're talking about a closed area, there's a definitive, unambiguous distinction between outside of the area and inside. I'll get to that more in a couple of minutes, but a closed area is a container. There's no question that some space is outside the container and some space is inside the container. So the direction out we always call positive, and the direction in we call negative, like with flux from now on. If the area is open, you can't make that easy convention, but if the area is closed, there's a clear out and a clear in. So out is called positive and in is called negative. All right. So we asked, what is the flux? The net flux out of the closed area surrounding the point charge. And what we found, oh, so we use the definition. There's the definition, right? We applied that definition and we went through like an argument last week, which I'm not going to repeat now, where we got an answer. We got that the net flux, the net electrostatic flux, double equal sign, in this case, was the value of the charge, Q, over that universal constant epsilon naught, right? And this was all using Coulomb's law. And this all assumes that the field lines are the way they were. Here, they're the red lines on the other drawing. Um, uh, yeah. And the point is, as abstract as this first example might seem to you, it's also a very sort of controlled, contrived first example. Like it's an example that's sort of as symmetric as things get. And so we got this result. We got a result that is remarkably simple. The result, the flux, remember, flux, the total amount of field times total amount of area. In effect, the accumulated impact of force per charge everywhere throughout that surface area, we found that the total flux was just Q over epsilon naught, that the flux was fully determined by the amount of by the amount of that point source at the center of the sphere. Okay. When I say it's very simple, I'm saying the result is remarkably simple, like so simple that it's worth remarking on. Yeah. Yeah. Like now, again, I'm not repeating. I mean, you have in your notes from Wednesday, like how we did this, but basically we integrated Coulomb's law with respect to dx. And then we found that a lot of the, 1 over 4 pi epsilon naught q over r squared, we integrated it with respect to ds. And a lot of things came out of the integral, and the integral ended up being remarkably simple. The integral ended up being 1 over 4 pi epsilon naught q over r squared times the total surface area of the globe, which was 4 pi r squared. So the r's canceled out is the big point. In fact, the fours and the pi's canceled out, and the r's canceled out because what really canceled out were 4 pi r squared. There was a 4 pi r squared on the top, excuse me, and on the bottom. Now, a couple of things. First of all, that is why, well, that cancellation is a very big deal. The fact that the 4 pi r squareds canceled out. First of all, it's why, just so that you know, I sort of warned you this at the beginning. Like we could write the electrostatic equation, the Coulomb's law. We could write it that E equals K Q over R squared. That would be like writing gravity field, G, lowercase g equals capital G times capital M over R squared. Like we could just keep the constant really simple and call it K. But the reason we don't, the reason right from the get-go that we write the constant in a complicated way, that we write it 1 over 4 pi epsilon naught, is precisely in anticipation of this, is to get those 4 pi's to cancel like that. Because the thing that is not up to us, that we can't contrive, because the r squareds cancel. And it's really huge that the r squared cancel. What it means that the r squareds cancel, what it means in English is that the total flux, the accumulated effect of field throughout some globe of space centered on a point source, the total effect of field seems to be the same whether the globe is really large or really small. Like that's what we're saying here. It doesn't matter the size of the globe. The total flux, the total effect of field on the space, the total number of arrows passing through the space, total number of field lines, is the same no matter how big the space is, or in this case of a sphere. First of all, that mere fact that the flux is independent of the size of the sphere is partially a hint as to why we care about flux anyway. Like I sort of warned you of this. When we move from field to flux, when we start paying attention to flux rather than field, it's like I mentioned, it's very much like the move from caring about forces to caring about work. We're in that we're integrating a dot product. Why? We're looking at the accumulated effect of some force or force per charge on a space. We're moving from a pixelated picture to a smooth regional picture, right? And that in itself has advantages. We're sort of zooming out, in effect, when we move from a derivative to an integral. But also the hope is that something like what happened when we moved from force to work, we then found that work transfers energy, right? I mean, this is back earlier in the work. When you do work on a system, you transfer energy to it, and energy ends up being this measurement that remains constant even when lots of other measurements don't remain constant. Like energy, mechanical energy remains constant even when velocity or position change. So it's a constant underlying variation. And that's really what we're always looking for in physics because we're trying to make predictions or retrodictions. So even when things, and it's hard to make predictions when things change. So we're always looking for something underneath the layer of changes, something that's remaining fixed below the surface that we can latch onto and drive our predictions, right? So something like that seems to be happening with flux when we integrate the field across a space. We get this concept called flux, which seems already to be having some kind of property like that. Like it seems like the flux doesn't change whether you look at a big, I mean, the field strength does, but the flux does not change whether you're looking through a small globe centered on a point source or a big globe. Okay, so first of all, that right there is a bit of a hint as to why we care about flux at all, because something about it is very simplifying to our calculations. But now one might ask, wait, why does that happen? Or like, why is the flux constant? Well, and I sort of mentioned this Wednesday, but let's mathematically, the flux remained constant for a sphere because the 4 pi r squareds canceled. The 4 pi r squareds canceled, specifically the r squareds canceled. What does that mean physically? I mean, because remember again, flux is field times area. So you'd think when you're looking at a bigger and bigger area, all other things being equal, you'd think you'd be getting more and more flux. And you would be if all other things were equal. But what we're saying here is all other things are not equal. In this case, as you go to a bigger and bigger sphere, you're getting more area, but you're getting weaker field. As you get farther and farther away from the point source, the field is weaker and weaker. It's weaker and weaker at the same rate as the sphere grows bigger and bigger. The surface area of a sphere is 4 pi r squared, and Coulomb's law is E equals 1 over 4 pi epsilon naught Q over r squared. Right? Like the field gets weaker as a function of r squared. The surface area of the sphere gets bigger as a function of r squared. So the field gets weaker exactly in the same way that the sphere gets bigger. So that's why. So when we say they cancel out, we're literally saying, yeah, you got bigger area, but you got weaker field by the same amount. So your flux is the same here or there. Right? I mean, it's like anything else in physics. Like, and you should stop me if any of this doesn't make sense or whatever. But in a way, if you are with me, in a way that might make so much sense to you that you might be like, oh, like duh, like I don't even know why I didn't think of that before. Or like I don't know what you're thinking, but I mean, it seems almost like, oh yeah, self-evident. But you know what? Right, it all is hinging on the fact that the field law here that we're talking about has r squared in the denominator. And the surface area thing has r squared in the numerator. Well, 2 points about that. Number one, if this does make sense to you so far, and please stop me if it doesn't, but if it does sort of, and I will turn the page a minute, I know it's like, anyway, if it does make sense to you, what it does for me partly is like it's all hinging on the fact that the law, the field law was inverse r squared. So in a way, what it says to me is, oh, wait a second. When we first looked at gravity, it was GMM over R squared, or field of gravity was GM over R squared. And then when we first looked at electrostatics, it was constant times Q over R squared, or the field was constant times Q over R squared. Like, like that was intimidating and weird to me at first. Like, oh my God, R squared in the denominator, that's like a complicated piece of math. Like, I have to deal with that now. And then it happened twice, like with both of these forces. But you might have noticed, like both of these forces, and I think we said weeks ago, gravity and electrostatics, they're both fundamental forces. They're both forces that occur with no activity required, right? You just stick a point of mass somewhere in space and it creates a gravitational pull that gets weaker and weaker in all directions as a function of r squared. Like it doesn't have to, the mass doesn't have to move, it doesn't have to touch anything, there doesn't have to be any material contact or intervening medium. And if it is, the force just passes through, like somehow automatically masses just pull on each other through empty space, fundamentally as a function of inverse r squared or as an inverse function of r squared. And then electrostatics, same thing. The other force that we know about so far that is action at a distance, the other force for which we associate, with which we associate a field, right? Like it's not a coincidence that we talk about gravitational fields and electrostatic fields, but we don't talk about friction fields or tension fields because the concept of field goes along with fundamental forces, goes along with forces that seem to be communicated or transmitted through empty space. They're relying on some sort of information interchange through empty space. So we're forced to start thinking about information existing in empty space. We call that a field, right? So the two forces that are fundamental in this way that just act automatically through empty space, they both have fields associated with them, and they both have this inverse r squared formulation structure. Now, what I'm saying is, oh, this is why the flux helps us see why, because it's almost like a duh once you see it, maybe, or in that the point is, if you put a charge at some location in the lab, it's pushing out on space equally in all directions. It's pushing out in all directions. Space is symmetric in all dimensions. You have a dot here. It's not asymmetric in any, it has a zero-dimensional asymmetry. It's just a dot. So it's pushing out the same way in all directions, but getting weaker and weaker in the same way in all directions. So its influence is spreading out through space in the manner of a sphere, of course, right? And so it makes sense that as the sphere gets like the rate in which these lines spread is exactly the rate at which they spread out from one another. Remember, the density of field lines is the way we represent strength of field. So, of course, these lines in three-dimensional space are spreading out at exactly the same, are getting weaker at exactly the same rate that they are spreading out, making a bigger sphere. Do you see what I'm saying? This is why these laws are inverse r squared laws, because these laws say dots spread their influence through space like as though creating spheres of influence, you might say. I don't know if you follow that or not, but that's what I'm saying. So I'm saying this retroactively sort of starts to make some sense at it. I'm saying the cancellation is driven by the fact that fundamental field laws are inverse r squared, and the surface area of a sphere is 4 pi r squared. And that is not a coincidence. Like they cancel out because one thing had to be true if the other thing were true. By the way, quick, I'm going to move on. I promise I'm going to move on now. I'm watching the time. Oh my God. But also, sidebar, if you're following this at all, remember I'm saying, well, am I going to say? I mean, a closed surface is like the boundary. Do I want, well, I'll just say it. Like, why is the surface area of a sphere 4 pi r squared? Well, 4 pi r squared is the skin of a sphere, right? If you added up all of those skins, if you integrated, if you take that boundary and like spread it through the entire space that it surrounds, you get the volume of the sphere, right? What's the integral? I'm just asking. I mean, I'm not asking. What's the integral of 4 pi r squared dr? It's 4/3 pi r cubed, isn't it? You see what I'm saying? It's all of this fits together. And same thing, if you didn't catch that, don't worry about it for the minute. But it's the same thing with closed paths and areas. The circumference, I'll do it the other way. The area of a circle is pi r squared, right? Take the derivative of pi r squared with respect to r. The derivative of pi r squared is 2 pi r. That's the circumference, the closed loop that is bounding the area. It all actually, okay, I'm going to move on, but this crap actually makes sense. That's like my, oh, what do you need to know right now? If you didn't catch that geometry calculus connection, don't, even though that's what this all is, don't worry about that for the minute. But what I do want you to see, and I'm going to turn the page. What I do want you to see is that the flux, the net flux through a sphere, excuse me, the net flux through the surface area of a sphere centered on a point source radius r, is independent of the size of the sphere. The flux is just charge divided by that universal constant. And don't get by, and the constant is just a constant. Like it's just a unit converter. I mean, if we were willing to measure in different units, we wouldn't even need the constant there. So I'm saying the flux is fully determined by the charge. Okay, but we can go on. I mean, that's what we see so far. But now I want to see, so that's if we draw a sphere, or if we picture a sphere around the point source. That's pretty simplifying. I mean, of course, spheres are very symmetric in all the ways I was just like yelling about. So, I mean, what if it's not a sphere? What if we wanted to know the flux through some container, some closed surface that wasn't a perfect sphere? Like, does that, then does the excitement of this result go away? Well, I would have thought so. I would have thought this whole thing hinges on the perfection of a sphere. But here's what's wild about it to me is that what makes a sphere is it's the locus of points in three dimensions, all equidistant from a point. In other words, what makes a sphere is that that there is a thing called r, a radius, which is the same length everywhere throughout the sphere, right? Well, so if imagine that this sphere that we're surrounding the point source with, imagine that's made of clay or something. So now we start playing with the clay and warping it or bending it, like poking it so that little parts of it like are bigger than R or like are at like 3R or so, and other pieces are smaller than R, like a half R or something. And so it's like a deformed sphere now. Or maybe we deform the sphere so much that we turn it into a cube, like we really deform it. So we've got like corners and stuff. Do whatever you want. We're now totally departed from a sphere, or at least a perfect sphere. But how are we departed from a perfect sphere if we play with the clay? Well, we've made a shape, and assuming we still keep it as some kind of closed surface, some kind of container, if we play with the shape of the container, all we're doing is violating the condition that R is the same everywhere. We like have an R here that's like 1 meter, and there R is 3 meters, and there it's two, right? But we just decided that R didn't matter. That the farther out you get in R, if you square it, you're making a bigger surface area. But if you square it, you're making that much weaker of a field. So we just decided that the flux was independent of the size of R. So if we make R change throughout the shape, who cares? It's going to be it would be like a little bit, it'd be like this section would be a sphere of radius 4 meters, and that section's like a sphere of radius 5 meters, and that one's 3. And we just said it doesn't matter what your radius is. So, I mean, that's a fast argument. That's not a strictly rigorous proof, but one can do a strictly rigorous calculus or not like geometry proof with cosines of the angles and stuff, and see that what I just argued is in fact true. And what I'm saying then is that once you decide that the size of the sphere doesn't matter, then it actually follows from that it doesn't need to be a sphere at all. Neither the size nor the shape of the container will affect the total flux through that container. That's what I'm saying there. And I'm going to go on. I'm going to say now, once you agree with that, so I'm saying evidently the total flux or the net flux is independent of shape. But now we can go even further. If the surrounding shape doesn't need to be a sphere, then in other words, if it doesn't have to be symmetric at all, right? It doesn't matter what R is doing. We just decided. I mean, that we did mathematically rigorously. It doesn't matter the size of R. The size of R, in other words, does not affect the flux result. So if that's true, then symmetry is not required for the total amount of flux to be fully determined by the total amount of charge inside the container. Then if symmetry is not even required, then it doesn't even matter if that dot of charge is at the center. It could be off center. Like what? I mean, it doesn't make any difference apparently. because again, it would be like the R would be small over here and big over there if you put it over center, off center. So evidently, the total flux, the net flux coming out of some closed surface evidently is independent of the size of that closed surface, independent of the shape of that surface, and independent of the orientation of that surface with respect to the charge point inside it. But now, stop me if I'm going to, but if that's true, if it doesn't even matter that the charge in, like we started with a very simple example on purpose, a very symmetric example, and we got a very nice, simple, elegant result that seems almost like exciting or usable at least. Now what we're saying is we got that result from very simplifying assumptions, but even if we relax the assumptions, it seems like we don't change the result or the mechanism underlying the argument. So now I'm going to go a step further. If the net flux through a container is fully determined by the amount of the charge point inside the container, and it doesn't matter the size of the container, and it doesn't matter the shape of the container, and it doesn't matter where that charge is in the container, like it could be off kilter, off center, then 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 apparently that's true. That would be true for each and every bit of charge we might have. Like you could have one piece of charge over here surrounded with a container. The total flux through the container is boom, is just Q over epsilon naught. Then you could have another charge over here, right? Uh, the total the total flux, sorry, then you have another point of charge over here. Like this one might have been like 1 coulomb, and this one might be 2 coulombs or something like that, right? So you have another charge over here surrounded with any kind of container you like. The total flux through that container will be fully determined by this 2 coulombs, right? So if that's true for each and every individual point that you can imagine, and if it doesn't matter where the points are in relation to the containers, then why can't we put a bunch of points nearby each other? And instead of drawing an individual container around each one, couldn't we just draw one big container around the whole bunch? And wouldn't, if all these prior results are really true, which they are, I'm not tricking you, I'm just trying to explain it in English. But if all of these prior results are true, that for each arbitrary point of charge, the net flux through any container surrounding that charge will be fully determined by the amount of that charge, then put any amount of charge you want together in any way you want, like make a cow out of protons or whatever, have like a bajillion protons in some bizarro shape, surround that bizarro shape in any bizarro shape you want. And what we're arguing here is that the net flux through the enclosure will be fully determined by the sheer magnitude of charge that you enclosed, period. That's what we're saying. And and if you want to sort of stay with me, which I hope you are, don't try too hard yet to care about why we would care. I mean, why we care is we like when things are constant and we like when things are simple. I mean, that's like the simple answer. But don't get too bogged down in why this would matter or what this would be useful for just yet. But see if you could just follow the reasoning that I'm saying so far. Well, I'm saying this. Yeah, okay. I'm saying apparently we can use the result that we got for the seemingly super simplified, super contrived, super controlled example of a point with a sphere around it. Like that's what we started with. Apparently, what we found, definitely what we found there was that the flux through the sphere, the flux through the surface area surrounding the sphere of radius r centered at one point of charge, we found that the flux was just the amount of charge itself divided by a constant, which really means in English, since the constant is a universal constant, really means that the total amount of flux, the total amount of field lines, the total effect of field throughout the entire surface of the globe surrounding that point charge was fully determined by how strong that point charge was. Like that's what we were saying in that simple example. Now we're saying, you know what, that simple example it actually contained all of the information that we needed that could possibly apply to even the most complex example. What we seem to be saying is through any closed surface, So the closed integral now, remember we did this with, right? We had path integrals. We had integral of dot product, force times displacement was the integral of work. But then we introduced this thing where sometimes we calculated work over a closed path. And we said whenever the integral over a closed path, a round trip, was zero, we called that a conservative force. Similar thing happening here now. Similar, not the same, but similar. We're saying, okay, from now on, like flux is the integral of field throughout area of any kind. But what we seem to be concluding here is that as long as that area is closed, as long as you're looking at the total amount of field lines going through some container, coming out of some closed area, some container, we seem to be concluding that the total amount of the net electrostatic flux emanating through any closed surface anywhere in the universe is equal to the Q enclosed. What that says is Q parentheses ENC. ENC stands for enclosed. I'll write it. I've written it on the next page. You'll see that. Um, Divided by the constant. The total amount of flux through any close. So you pick any container in the universe. It doesn't have to be made of material. You just picture any spatial container, any closed surface anywhere in the universe, and you want to know how many field lines are coming out of this container, how much field is acting all throughout the entire wall of this container. Well, what this law says, this generalization, this law called Gauss's law says, if you want to know the total number of field lines through any container in the universe, it's fully determined by the charge enclosed by that container, enclosed by that closed surface. In other words, okay, so that's the law. That's a law. And it is literally like it's literally always true. It's not a triple equal sign because it's not the definition of flux. It's a result, it's a discovery, but it is 100% true all the time. It's again, whatever you could picture, and I'm going to try to make this more physical in a minute. We're not going to do more examples. We're just talking about this because it's such a big result. But I'll try to give you a different way of thinking about it in a minute, but but if you were picturing what I was saying at all last Wednesday, if you could picture that the total flux through this sphere was the same as the total flux through that sphere, which in effect means the total number of field lines going through this sphere was the same as the total number of field lines going through that sphere. Well, I'm saying that's always true for any container, for any container. Specifically. Well, okay, so in English, I'm saying sorry. Well, that's the log. I just wrote it on the top. I'm saying the net electrostatic flux out any closed surface is fully determined by the total magnitude of net charge distributed throughout the volume enclosed by that surface, right? So I'm saying the left side of the law is asking you to picture some kind of closed two-dimensional region of space, like a skin, uh, of anything. It could be a ball. In this case, we're talking about a ball, but it could be a cube, it could be a cylinder. You picture the skin, the container of some space. The total number of field lines coming out of that skin is fully determined by the total number of charge points within the container. So the left side is is asking you to look at a two-dimensional region, and it's saying the stuff through the two-dimensional region is fully determined by all the stuff in the enclosed interior three-dimensional region. I'm going to keep going. Some of you, well, if you're anything like me, I mean, hopefully you're still paying attention. I love this. I'm sure you are still paying attention. If you're anything like me, this might seem very, very abstract. I just want to pause for a second. I'm aware that for some of you, it's like wah, 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 wah. Because I'm talking about space, like it's all about space. There's no concrete example, really. I mean, but the examples are of very abstract things like field lines through space. And I'm going to try to make it more concrete in a moment or so. Bear with me. But I also want to say there are some of you in the room, and I have no idea who you are, but there's something about this thing that I'm saying that some of you might be getting it, and you'll know you're getting it if you're thinking, wait, I think I get it, but I don't see what the big deal is. Like, I feel like I'm getting it, but I must not be getting it because what I'm thinking is so simple that I don't see why he's making a big deal of it. If you're thinking anything like that, and you'll see in like 10 minutes, then you probably are getting it. Like everything in physics, there is something very abstract at first about what we're talking about. And then when we really, really look at it hard enough and make enough analogies, something about most great physics ideas, eventually, the minute it comes to make sense, it seems so obvious it doesn't seem worth mentioning. Like if you're in that space right now, please remember that's the nature of physics. It probably means you are getting it. And then my job is to show you why it is worth saying. Like if you're thinking, I guess I always knew this, I just didn't care. Fine. Then my next job is to show you why to care. Okay. And a hint is because anytime we discover something that's constant in physics, it's really powerful. Okay. But what I'm trying to say is that the number of field lines through a container only is dependent on the number of things inside the container making the field lines. That's what I'm saying. And if you think, well, yeah, then you're with me. Don't I mean, but if you're thinking WTF, okay, either way, stay with me. Just to summarize what I'm saying so from what I'm saying so far right now, I think this I think everybody's getting at least the words, but let me just be ironclad about it. Gauss is saying if you picture any closed surface in the universe, any container, right? I literally like closed surface, like skin of orange or shoebox or tennis ball can. You picture a closed surface somewhere in space, and you want to know how many field lines are coming out of that surface from within, like how many net field lines are coming out, i.e., maybe some are going in as well, but we're subtracting those and just what's the net number of lines coming out of any container. What we're saying is that answer that we would get would be independent of the size of the container, independent of the shape of the container, independent of the configuration, or in other words, the shape of the charge within the container. Like it's just right. It doesn't matter how the charge is distributed within. It's just the total amount of charge within will determine the number of field lines. And we're also saying something I never mentioned yet. Hello. Something I didn't mention yet is, but is evident if you're following this, is we're also saying that the total amount of field lines coming out of some container is also independent. I'm on number 4 right now, is also independent of any charge that might be anywhere outside the container. Because I mean, all charge causes field. Every point of charge in the universe causes field lines to radiate out symmetrically in all directions, right? So, I mean, all charges are, so the universe is very complicated. But 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 what we're saying is once you're looking at a container, if you want to know how many field lines are coming out of that container, you don't have to worry about any charges anywhere outside the container. You only have to count up the charges inside the container to find the number of field lines coming out. The reason for that, the reason you don't have to look at any charges outside is because any charge outside sure will create a bunch of field lines. And any number of those field lines might start busting into your container for sure. Like here's my container over here. Here there could be a charge over here. So it might make a field line that goes up and fluxes into my container at some angle. That certainly could happen. But then necessarily, if it's a line, if it's a field line that goes on forever as field lines do, right? And if the container doesn't go on, it's a closed surface, then this line, if this field line, if it enters the container, it has to eventually exit the container. So it will create net flux of zero. Right? Any charges outside the container, the closed surface, will create no net flux. So I'm saying right now, and again, if you're with me, the more you're getting what I'm saying, the more you might be thinking, oh, is that all he's saying? Like that's it, then you're with me if you're thinking that. All I'm saying is I'm saying points of charge create field lines. Every point of charge creates a number of field lines that radiate out infinitely from it, an infinite number of them. When we draw, we usually pick a scaling factor. Like we say, like for every 1 bit of charge, 1 coulomb charge, there's like, we draw like 8 lines. So every 1 point creates 8 lines. I'm now saying if you have any container in the universe, you want to know how many lines are coming out of that container, all you got to do is count up the number of dots inside the container, or if they're really close together, count up the number of coulombs of charge inside the container. You don't need to know how they're distributed. You don't need to know about any charge outside the container. You don't need to know about the shape of the container. You don't need to know about the size of the container. If you just know how much charge is inside the container, you will definitely know exactly how many lines are fluxing out, busting out of the container. If that's a statement, that's Gauss's law. If you are thinking, oh, I get it, but that's so stupid, like obviously, then you really get it. I mean, it's not stupid. But if you're thinking it's stupid, then you get it. Because yes, there's some, once you say it enough times in your mind, it starts to become self-evident. I'm saying the crap that's coming out of a container is fully determined by what's in the container causing the crap. Like that's all I'm saying, right? But trust me, it is important. Um, Note a couple of things. Note a couple of things about this. And if you're still not getting it, still just hang with me. Hopefully we have 15 minutes and we're not doing more examples or anything. I mean, on Wednesday, I will continue to cook through the homework. I mean, I'm not cooking, but I will continue to I will be more concrete about showing you how this gets applied, this result, as in the examples of the homework. Okay, just right now, I just want to show you what the yeah, wait, do we need to enumerate and prove? Right. Good question. So I'll pause for a second. I'm looking at the time. I assume HM means HW, but yeah, so the whole point of homework 7 is that okay, right. The whole point of homework 7 is that in the first part, you just calculate the flux through a sphere centered at a charge and you get the result. And then it sort of asks you, like, make an argument to generalize why this would be true in general. And that's like what this whole, so that part is what this whole class has been, how you can argue in English and convince yourself and convince me that the result that we get, Q over epsilon naught, the result we get for a point surrounded by a sphere, that result actually would be true even if the situation were far more complicated than a point surrounded by a sphere. Once you make that argument, then you have argued for the truth of Gauss's law. And then the rest of the homework, you don't re-explain any of that. You don't rederive any of that. You use Gauss's law for the rest of the homework to compute the field strengths and directions in the various examples throughout the rest of the homework. Oh, is that a great? Okay. Well, to everybody. So first, you're sort of in the beginning of the homework, you're sort of arguing for the truth of Gauss's law, which is what these last two classes have been. And then the rest of the homework, you're using Gauss's law, you're applying it. You're not calculating flux anymore. You're using the concept of flux, using the fact that it's always going to be the same in order to compute various E fields in the rest of the homework. How you do that, I'm not saying it's easy. I'm not saying it's obvious. I'm saying that's what I will show you examples of next class, Wednesday, and that's why I've just extended the homework, I guess. Okay, so hopefully that looks like she just did a thumbs up. So now, just in the last 12 minutes of this, let me say a couple more things about what this Gauss's law means, why it's you could see I it's just really weird. Like, and again, I hated it when I was in college. Oh my God. I mean, I remember I was like so like, what is this? Like, why do I? And so maybe part of the reason I love it now is just because I love the fact that now I get it. I mean, this happens, but I don't think so. I think I really love it now because it really means something interesting. About unthingy things. So what does it mean? Or what is all right? So first of all, note, okay, here we go. Note one thing that I essentially already said, but I want to be explicit about, which is that we're sort of making a geometric, we're making a geometric assumption here. I don't mean assumption like it's not true. I just mean like it's in the background of our thinking and we're using it. And it's like many other things. We may have sort of always known this, but we just didn't know that it was a thing or that it mattered, which is that a closed one, I mean, there's two types of regions, closed and open. I mean, two types of regions of space, closed and open. But there's also a different distinction in space. There's bounded and unbounded regions in space. For those of you that like want to care about physics or want to know what any of this has to do with like anything that's cool in physics or the universe or anything, when I use words like what I'm really trying to say is, there's different types of infinity. People talk about the universe being infinite and stuff like that. But that gets confusing fast because there's at least two different ways we could be using the word infinity. When we say that a space is infinite, we might mean that we might mean that the space is unbounded, like it has no boundaries at all, like a line segment is bounded, right? A line segment is bounded by 2 points at the end. So you can like be a mosquito, be walking along a line segment, and then eventually find yourself not, you hit one of the points, and now you've walked off the line and you're on the piece of paper or something, right? So a line segment is bounded in the sense that there's a limit to it. And eventually, if you keep going in the same direction in that space, you're eventually going to be in a different space. That's bounded. Whereas a line, as opposed to a line segment, a line is unbounded, right? Like you keep walking forever. You never hit the end or the limit of it. That's unbounded. In a way, that's often what people picture when they're like, oh my God, does space go on forever? Like, and you can picture it in one dimension or two dimension or three dimension. Like, is it, without saying it, they're saying, is space unbounded? It's infinite. Oh my God, like I would just never hit a limit. Whoa, that's crazy, yo. But that's bounded versus unbounded. In a whole other side of my brain, there's a different way to distinguish spaces. You could talk about a space being open or closed, right? We were already saying. And think about that now. Like an open line segment is bounded. So in that sense, it's finite, like I just said. But if you close up the line segment and make it a closed path and you're a mosquito, well, if you're in that path, you could keep walking forever and never fall off like us on the earth. Like I could walk along the surface of the earth and I could just keep walking or driving and driving and driving and driving and never hit a boundary. It's not bounded. Not because it's not because not in the sense that a ray or a line is unbounded, but in the sense that a loop is unbounded, right? So I mean, in other words, that's another way a space can be infinite. So things are closed versus open. They're also bounded versus unbounded. And the relationship is this. A close, so, oh, well, so sidebar, so that you care or whatever. When people say the universe is infinite, like you could just keep going forever, it's not clear. That may be, well, presumably that is true, but it is not at all clear whether that means the universe is going on forever because there's no, in the sense of unbounded, or is it in the sense of open unbounded, or in the sense of closed? Like, is the universe, would you go on forever because you're really walking around the skin of some four-dimensional space without realizing it? Okay, that's like a psychedelic, but that's like really a question. Like, we don't know if the universe is open or closed. Um, and either way, it would be infinite, but it'd be very different kinds of infinity. But anyway, what I'm saying here is that a closed one-dimensional region of space is always the boundary. It always bounds an open two-dimensional region of space. Like, whoa, that's a mouthful. But again, you knew it. You just didn't know you cared. I'm saying like a ring. Well, let me back up. Like I'm saying like a coin, a disc. Okay, that's an open area. It's an open area that is bounded. If you were a mosquito walking around on a disc, you'd eventually hit the edge you'd eventually hit the edge of the disc and fall off. There's a boundary to that disc. So it's open, but it's bounded, right? I know this is a lot in a way, and yet it's not. What is the boundary of that open disc? The boundary is a closed path. The boundary of that open area is a closed circumference. So closed one, right? And the closed circumference is not bounded. It's bounded. Like you just keep walking or walk, but it itself is the boundary to an interior space. A closed one-dimensional path is the boundary to an open, a closed one-dimensional region of space is the boundary to an open two-dimensional region of space. Similarly, a closed two-dimensional region of space bounds or is the boundary for a three-dimensional region of space. Only in, right? You see the parallel? Hopefully, maybe. I know, again, in a way it's a lot, and in a way it's like nothing new. It's just weird that it matters, and it does matter. Um, the difference between those two statements. So I'm saying there's some kind of relationship between n dimensional spaces and n minus one dimensional spaces. There's a relationship that continues like this. And by the way, the boundary to a one-dimensional region is zero-dimensional regions, points, right? I mean, it goes on like this. But the subtle difference is that a closed two-dimensional region of space bounds a unique three-dimensional region of space. Maybe that's just because I can't perceive or measure at this point in my life or in the history of physics. I don't know what it means to perceive or measure four-dimensional spaces. I'm not saying they don't exist. I'm just saying I don't have access to them. So my world is three-dimensional. So when you give me a closed two-dimensional surface, it is automatically right away unambiguous what that surface is bounding. It is bounding a very specific, unique, one and only volume. And that's the nature of Gauss's law. It's saying the stuff coming out of the boundary of that volume is fully determined by exactly how many charges are in that volume. All you got to do is count up the charges in the volume enclosed by your skin, and you'll know all the stuff coming out of your skin. And you can always do it. You can always count up those number of charges in the enclosure because the enclosure is unambiguous. I mean, if you look at a tennis ball can, it is clear how many tennis, like what's the difference between inside the tennis ball can versus outside the tennis ball can. And if three balls can fit in the tennis ball can, then that's the end of the discussion, right? So first of all, I'm geometrically sort of positing that a closed two-dimensional region of space is the boundary for a unique three-dimensional region of space. So then Gauss's law is really like about that. In a way, Gauss's law is asking you to focus on what's happening at the boundary. It's saying what's busting through the boundary of a volume is fully determined by what's inside the volume, causing the bust out. In other words, what it's saying, this is the last page. Oh, well, okay, well, second last. What is Gauss's law really saying? If you've lost me, if this all seems too not physical, what we're really saying is, like, I guess I'm sorry, it's the third to last. Okay, it's 3 minutes. I'm saying, look, remember, flux is field strength multiplied by area. Amount of field, how strong the field is times the area. Now, that's a little hard to picture until you remember that if we're picturing fields, we're picturing field lines. And the number of field lines per unit area is the strength of the field. Magnitude of field is represented by how close the lines are, right? So number of lines per area is field strength. So when we multiply field strength by area, we're actually multiplying number of field lines per area times area. It's not a coincidence, and it's not a circle. I mean, it sort of is. In other words, all this abstraction, whenever I say flux, all I'm saying literally is count the number of lines. Like in our original example, you have a point here. We have a scaling factor. We're drawing 8 field lines from every one point. So we surround it with a sphere. And to ask what's the flux through the sphere is to just ask how many field lines are coming out of that sphere. And the answer was 8. And then what we're saying is, well, if you make the sphere bigger, how many field lines are coming out? Still 8, right? I mean, duh, right? And then what if we make the sphere into a cube? Still 8. What if we shove the charge over? Still 8. We're just saying every bit of charge causes a certain number of field lines. So the number of field lines, so to ask about flux is to just ask how many field lines are there? Like literally, that's why we like flux, because ultimately, as abstract as it sounds, visually, it's super concrete. Flux just means the number of these freaking lines. And we're saying that number of lines is independent of anything other than the number of things causing the lines. So what we're really saying in Gauss's law, this is the last page, we're really saying, like, and if you've been thinking this or anything like this, then you're right. We're saying, imagine, and I know there's 1 minute left. This is it. Imagine there's a sprinkler shooting jets of water in all directions, right? You try to catch the water with some tarp or some tent, right? It doesn't matter what the shape of your tent is or what the size of your tent is or anything. The amount of water that you're going to catch on the interior of that tent is fully determined by how much water came out of the spigot. That's it, right? Because everybody takes for granted water is neither destroyed nor created. Like there's not going to be any spontaneous droplets of water that just appear in the air between the spigot and the tarp. So the number of jets of water is fully determined by the number of sources of water. That's it. It's obvious. That's all we're saying. It's obvious when we're saying it about water, I think. But the depth of this is what we're saying in the end is field lines act like water. Exactly like water. Field lines are not created nor destroyed except by point sources. And I know it's 420, but here's why that's interesting. Well, first of all, it's mathematically very powerful. But second of all, if you understand that I'm saying field lines act just like water, then you're with me and you get it. But just know that that's a pretty deep thing to say because field lines are just information. They're not thingy things. They're just raw information field lines. So what we're saying by Gauss's law is that raw information in space acts like stuff in space. It's conserved. We're saying information is conserved. It's neither created nor destroyed spontaneously. You only get information from charges. So the number of field lines through an enclosure is fully determined by the number of charges. Field lines are unthingy things, but apparently they act just like thingy things. That's the conclusion. Okay, we'll do more of this Wednesday. You've been very patient. Thank you. See you. Call me if you're having anxiety or whatever. You know what I mean about academics. Okay. Thank you. Bye. Yes, have a good day. Yes, have a good day.
Bye, thank you.
Thank you. I promise I'm doing your tests soon, Skylar. Sorry it's taking so long. If you're there, I'm not recording. Am I recording? Oh, I am.